Okay, so good afternoon, everyone. Well, thank you for being here for this webinar. I think we have a very interesting set of speakers and presentations. So my name is Guilherme. I'm the technology advisor at Nucleareurope, and I manage the hydrogen task force. So before we go to the speakers, just a bit of housekeeping. So this webinar is recorded, so you'll be able to watch it later in our website. You'll be able to ask your questions during the presentation, so they will be answered at the end, but you can ask them whenever you want in the Q&A session. So please do not use the chat for the questions. Use the Q&A section because it's well, its purpose is that your mics are muted, so you will not be able to ask any questions by speaking. And at the end, we will send the presentations of the speakers that agreed to share them. Yeah, so that's it. So I will now like to give the floor to Andrei Goicea, which is our policy director here at Nucleareurope for a short introduction of the webinar. Andrei, go ahead.
Thank you very much, Guilherme. Welcome everyone to another webinar organized by Nucleareurope on hydrogen from nuclear power. Spotlight on EU-based hydrogen production is the title of this one. So this webinar proposed by the Hydrogen Nucleareurope Hydrogen Task Force. It's a very active task force that started 2 years ago as a necessity to cover this hot topic in Brussels, the discussions on hydrogen, but not only. And is it, I think, a good opportunity to thank to the task force for their active involvement in the discussion on the topic, to Aymen, the chair of the task force, to all the members, but also to Guilherme, who is supporting the work from Nucleareurope Secretariat. So hydrogen started to be a hot topic in Brussels, as I was saying. A lot of discussions were happening, especially after the EU hydrogen strategy was launched back in 2021, if I remember well. And even if we, with the 2040 climate target communication, the initial ambitious targets for 2030 was postponed somehow, I think that the hydrogen topic remained very high on the policymakers' agenda. This is the third in a series of webinars focusing on hydrogen from nuclear. And we are organizing, the topics and the discussions on of this webinar will focus also in the context of different investments that are starting all over Europe on hydrogen production. And I think that it's time for nuclear to also take share of this market and to be considered as an important player in the hydrogen production. In terms of future legislation, we have the Gas Package Delegated Act that will be crucial for this hydrogen developments, low carbon hydrogen developments, and Nucleareurope is working on it to achieve our goals of a level playing field when we are discussing about hydrogen production, but not only. So after this short introduction of this webinar, I would like to give the floor to the next speaker, Félix Moldován, who is the Atomic Questions group member and energy representative from the Hungarian Permanent Representation. We know that Hungary will hold the next presidency, and we would like to thank very much to Félix to join us and to be able to join us, especially that we know that exactly now today the Energy Council is ongoing. So there are a lot of things going on in Brussels. Félix, the floor is yours.
Thank you very much. Thank you for the invitation. I think it's a very, very great event, great and timely event. As Andrei has said, the Energy Council is currently ongoing, which means that after giving my short intervention, I will have to leave you and sadly miss out on the discussion. But if there's any questions you would like to address to us as the incoming presidency, I'm stand ready to answer them. Just briefly, Andrei has already mentioned the big milestone, I think, as of late, in terms of hydrogen was the adoption of the gas package. I'm sure you know the ins and outs of the package. The directive will apply when it's the moment it enters into force, and the member states have a 2-year window to implement the directive, and the regulation will has a 6-month period after which it will enter into force, and it will have to be applied. Most likely that's going to happen in the first months of 2025. Another big element, the details of which I believe are still under revision, is the hydrogen bank. As far as I understand, the Commission plans to launch a second tender towards the end of this year. This is public knowledge, but I have informal confirmation that that they're actually going to go ahead with it. Now, one of the most important upcoming pieces of legislation, Andrei has also mentioned, it's the Delegated Act on Low Carbon Hydrogen. We've been waiting for a while for this piece of legislation. And as far as I understand, there's still only a 50% chance that it will be published in the coming months or not. We will hold a workshop at the Hungarian Permanent Representation on the 8th of July, specifically on the topic of this delegated act. The hope is that we can have some input. We could gather some input from the participants that then we can channel into the Commission. So fingers crossed for the Delegated Act on Low Carbon Hydrogen to come out. But that's unfortunately out of our reach. In terms of hydrogen production per se, I'm sure you all remember the Repower EU plan, which says we need 10 million tons of renewable hydrogen produced in the EU and 10 million tons to be imported. Now, as far as I understand from the people I have talked to, we are very, very off from generating that amount of hydrogen. There was an estimate, I don't know if it's correct, but if all the projects that are currently in the pipeline, we would reach maybe 3 million tons, which is very shy of the estimated 20. So in that sense, and building on that, I think nuclear generated hydrogen will have a very important role in the upcoming period. Obviously, a lot will depend on the outcome of the European elections, on the commissioners that are in charge not only of the energy portfolio, but also on the environmental portfolio. So if everything aligns, then I truly believe nuclear and nuclear power generated hydrogen will be a lot more in the spotlight, or to be more precise, in the positive spotlight than it has been the case the last 5 years. So in short, policy-wise, the next 6 months, we're not planning any initiatives. It's an unfortunate time in that respect because the Commission is in transition. So no new legislative acts are expected in the next 6 months. But as I said, after the new commission is set up, depending on who gets the mentioned portfolios, things might speed up starting from the Polish presidency of next year. But, and this is my final thought, the momentum is definitely shifting. Nuclear energy is definitely being more and more accepted. More and more commissioners go to nuclear events, even to those organized especially to those organized by Nucleareurope. I think you had 3 commissioners at some point in one of your events, which was unimaginable a few years ago. So yeah, momentum is shifting, and if the pro-nuclear countries and the industry plays its cards right, I think a lot of headway can be made in the next term of the commission. We will definitely work on improving the acceptance of nuclear, and also we're a strong proponent of, I mean, I'm talking as Hungary, of hydrogen being generated not just from renewables, because we don't see that to be feasible, but also from other sources, including nuclear. So that would be my very short intervention. Again, I would like to apologize for leaving, but I do wish you all a very fruitful and good discussion. Thank you.
Thank you very much, Félix. I think it's very interesting. It's good that the next presidency of the Council of the EU will be willing to work towards low carbon hydrogen, specifically from nuclear. Thank you very much again, and well, I hope to see you soon. Okay, so now I will introduce to you the moderator of the rest of the webinar. This is Aymen Grira. So he is the chair of Nucleareurope's hydrogen task force, but I will let him introduce himself better and the rest of the speakers. Okay, Aymen, the floor is yours.
Yeah. So thank you, Guilherme. I have my hand. So good morning, good afternoon, everyone. Pleasure moderating this panel. Thanks, Andrei, for the introduction. Thanks, Félix, for the updates. I'm really happy to hear such a key message on importance of nuclear and also the combination of nuclear and hydrogen. So today it's the third webinar that Nucleareurope Hydrogen Task Force is organizing. I see that we have more and more people connecting, which is actually a good signal that this topic is becoming interesting, more and more audience and larger audience, and hopefully a lot of policymakers that will learn and ask questions that we would be very happy to reply back. So with me, we will have 3 speakers. They will be representing almost the value chain. So Fabio from Tractebel, please activate your camera. There will be also Nicolas from Genvia. Please activate your camera. And last but not least, Dirk from ULC. We will be trying to cover the full, let's say, topics from market, business, pricing, up to technology, and ending by example and illustration of projects in the field. My last thought before handing over to Fabio is the topic of hydrogen nuclear. It's really from a business-wise, but also from a technology and market-wise, it is justified. So the hydrogen, we all believe on hydrogen, and we all think that hydrogen is going to be a game changer in the decarbonization. But the nuclear still can play a role in a very short term because existing nuclear power plants are there, and they are producing heat and steam and electricity, and they are not maybe as leveraged as possible for the decarbonization. The demand is also justified. Hard to abate sectors, they are looking for massive production of hydrogen to decarbonize and to apply their strategy. And last but not least, from a cost-wise, you will see that the business case, it's really rational and doable. And I'm very happy to hear Dirk insight. So I will hand over to Fabio. My last request to the audience, please, if you have any questions, feel free to ask your questions at the Q&A and not at the chat. Please, at the Q&A. And we will be very happy to reply back to your questions. We will have a last part, which is 30 minutes. We will have for Q&A. And we will try to answer as much as possible questions. So the floor is yours, Fabio, and thank you for joining us today.
Thank you, Aymen, for the introduction. I will start sharing my slides. So my name is Fabio Nouchy. I'm a SMR product manager for Tractebel engineering. But here today, representing what we have done at Nucleareurope within the hydrogen task force. So we just produced a position paper on the domestic production of hydrogen. So the title of this presentation, and I would like to thank for the contribution the whole task force, in particular Aymen, Jean-François Dedin from EDF, and Emmanuel Gireza from ENGIE, and last but not least, of course, Guilherme, that is leading the task force. So Félix had done quite a good introduction, actually, of this presentation. So the first two slides are going to be actually a bit recapping what he said on the Repower EU ambitions for hydrogen production and imports. Then what we saw this year in 2024, the climate target. And then we will go a bit more into the, still being high level, going a bit into the more technical, so difference between imports and domestic hydrogen production. What are the differences and what are the pros on why we are pushing for domestic hydrogen production. And then, yeah, the nuclear part comes into play with pros and cons and an overview on the variables that are affecting the cost, concluding with the policy recommendations that we are giving in the paper. So this first part was quite well introduced, I think. The ambition from the 2020 plan was 10 megatons of domestic hydrogen productions, compensated with some 6 to 10 megaton of imported hydrogen. So this domestic hydrogen still requires a huge amount in terms of power, electric power, for the electrolyzers that will that are requested in order to produce this hydrogen, with a contribution to the final energy consumption that is quite reduced. And if we see actually the total energy consumption, we see a reduction, as in the assumptions there were a strong reliance of the electrification of the project, of processes that can be electrified and not use hydrogen immediately, directly, and especially energy savings. So this was the situation of 2020, and this year there was this position on what are the targets for the 2040 climate that has to be undertaken by the European Commission in order to get closer to the net zero at 2050. So the target is indeed a net reduction of 90% of the emissions. So very still very ambitious, which comes in hand with 20 to 35 megatons according to the different scenarios of renewable. It's stated clearly renewable-based hydrogen. So this is a domestic production. However, what came back indeed was a redimensioning of the production of the hydrogen production at the horizon 2030. So although we were talking about 10 megatons before, which seems in line with an ambition of 20 to 35 megatons. As Félix said before, the reality seems that both the demand on one side and the projects that are going to produce the domestically the hydrogen is limited to some 3 megatons. And still, this still not. So we are going to now dive deeper into the difference between imports and domestic hydrogen. So just to align ourselves, when we are talking about the hydrogen value chain, we often think about mostly the upstream part, so the generation of the electricity that is needed, or the fuel that is needed as a feedstock to produce hydrogen, the transmission of this, and the how to convert this fuel or this power into the molecule of hydrogen. We do not have to forget that indeed there is, let's call it a downstream part, which includes a compression and storage, and a transport part if the end user is far away from the production site. And of course, into this ecosystem, a very important part to play the off-takers. May that be mobility for future stations that are powered by hydrogen, for future vehicles that are hydrogen moved, or maybe those be heavy industry, for example, steel producers, or yet other like hydrogen as a feedstock for other chemicals, and we are speaking there, for example, about the sustainable aviation fuels. So what is tendentially what has been the tendency lately to look at the overall system in hydrogen production has been to leverage the existing infrastructure with some complementary development, of course, but by leveraging especially the production on those best-in-class renewable fields that usually are located not necessarily in the same place where end users are. So this comes with the up part, which is the fact that the upstream cost, like the production part, can be quite reduced because of possibility to connect directly electrolyzers with those renewable fields in areas where it is abundant. There is abundant solar power or abundant wind power, and to abate by that the upstream cost. However, the uncertainty and the impact on the downstream cost, well, that's the downside of it, which due to the expenses in terms of compression, storage, decompression again, well, transport, decompression again, and insertion in systems in the local network. So those are all aspects that can be avoided with, of course, domestic production. So we're already anticipating here the presence, like for who knows Tractebel, this is usually a small modular reactor in its place as a cornerstone, let's say, in the energy ecosystem of tomorrow. On one side, complementing with its flexibility the renewable energy, intermittent renewable energy sources, but also by complementing with the heat on one side, district heating or industrial heat. In any case, the point here is the possibility to be in proximity to the end user would heavily reduce the uncertainty and the impact of the downstream costs on the cost per kilo of hydrogen. So these this is not limited to SMRs, but everything that is a domestic production, may that be by conventional existing nuclear power plants, it has its advantage, and we will delve a bit deeper later on the upstream costs, on how to reduce that part, and what is its impact. So not only economical advantages on one side, the reduction of uncertainties, but also on the other side, the possibility that a domestic hydrogen production can have for the reindustrialization of Europe. Europe has seen in the last decades a very important loss of value from the industry in its economy. That comes hand in hand, unfortunately, with the loss of jobs that often they are high skilled, high value jobs in the manufacturing industry, and with that, of course, also economical losses. So the possibility of having an energy hub in which end users will capitalize from a co-located energy source, and with feedstock for their use of hydrogen that is produced nearby the site. Of course, it has a lot of implications in terms of security of domestic production. Again, jobs, overall energy efficiency of the whole system, and of course, this time the possibility of decarbonizing the economy, as it is our target to do. So if we go a bit deeper into the reason of using a nuclear source for hydrogen with respect to other competitive low carbon sources, we have we have, of course, consequences or contraries on one side, which are the possible restrictions on collocating the nuclear installation close to the plant. The high upfront cost. There is indeed a need for different funding system and financial systems in order to overcome this obstacle, and addressing on the side of the public acceptance. So these are all somehow aspects that are slowly being addressed, and that we hope for the future to let's say keep this balance towards the pros, which are the creation of local energy hubs. So as we spoke in the slide before, the limited so the aspect of using nuclear, the existing nuclear, this has really a very important impact that we want to highlight here. Nuclear installations would request a very limited capital expenditures, as in terms of co-locating hydrogen production close to them. So this is the second point. Existing nuclear installations could be a short-term solution to indeed have a massive production. And it has been studied, this is on Tractebel side, that at the level of co-locating in terms of hazards, let's say co-location hazards in terms of, for example, hydrogen risk of hydrogen explosions, that a small distance of a few hundred meters that would simply reduce the impact of this risk to zero. Other advantages that would come that are, let's say, more economical are the possibility of using the new technologies of high temperature electrolyzers under development at the moment. We will see later the presentation of Nicolas. The high load factor, and so this brings back a return on investment that is faster than the one for renewable energy sources, and so by that also higher efficiency, and so longer lifetime of the installation. Speaking of the electrolyzers, and here we depict different competing, on one side, low carbon sources, and so the 5 columns on the right, together with the gray hydrogen, which is the one on the left, the one that is let's say somehow the reference of it, together with carbon capture and storage, the renewable hydrogen, so the hydrogen coming from renewable sources, and 3 nuclear-based scenarios, in which one is short-term, 2025, by an existing nuclear power plants with existing electrolyzers, so low-temperature electrolyzers, and the other 2 projected at the horizon 2035. One with an existing nuclear power plant, the other one with a hypothetical SMR. And on one side, we can see the possibility of having a behind-the-meter solution with the new technology of high-temperature electrolyzer. And what I want to show here is the impact, considering that you may have a lot of questions in the slide before, the impact that these different parameters are bringing to this upstream cost of hydrogen, for which took a hypothesis of on one side the carbon tax, 100 euros per ton of CO2, which is impactful, especially for the gray hydrogen, at the level of the low carbon of the blue hydrogen, the one that is coming from carbon capture and storage. There, it's mostly the technology of carbon capture that is raising, let's say, the price for production. Renewable hydrogen, unless despite having the possibility of having a cheap LCOE, if you couple it behind the meter to the hydrogen production installation, so electrolyzers, with nowadays efficiency of 55 kilowatt hours per kilogram of hydrogen produced, the impact of the low capacity factor, so 2,500 hours per year, with respect to almost like around 8,000 hours per year that nuclear can provide, it's a big handicap for indeed renewable energy sources. So in the nuclear scenario 2025, we took as an assumption for the price of electricity. The impact of electricity is the most important, indeed, which could be in a scenario in which the plant is behind the meter, and at the same time increasing the efficiency with the new technology of electrolyzers would decrease by more than a factor of 2 the price of hydrogen. The last scenario, it's also one of the envisaged one. So with a hypothetical 80 euro per megawatt hour, we will see later on from Dirk's presentation a bit more also like in this case, in which we have indeed the most impact is on the electricity price, but there are perhaps ways to reduce that price as well. So I conclude then here with the policy recommendations that we have in the paper for the European Commission, the level of the importance and focus that we have to do, that we give on diversification on the approach to hydrogen production. So the importance of energy sovereignty. Indeed, this diversification it's practically highlighted at the end of this slide with the fact that the nuclear industry is asking for a technology neutral approach when we are talking about low carbon hydrogen. So all the technology sources should be treated the same way. So for that you need policies to support on one side finances for financial incentives, regulatory frameworks, collaboration initiatives, and the investments in the infrastructure by focusing on try to get the whole system more efficient. This means prioritizing the proximity to end users with an eye on the cost effectiveness. And last but not least, indeed, to provide some resources for research and development initiatives, so that both high temperature electrolyzers and SMRs could see the light of the day at the moment that is most requested, so as soon as possible. So this was it for this introductory presentation, I'd say, and I give back the word to Aymen, and then to the next speakers.
Thank you very much, Fabio, for the insights and for the summary of the paper that has been published, communicated by Nucleareurope, in which you have been very active. First, let's say, I think you summarized very well the importance of the role of nuclear in the hydrogen production in a domestic way, in a very special context of Europe today. And my question, I do have some questions, and the audience has some, let's say, many questions, good ones. I will highly recommend that you take a look. And once again, we will answer all the questions at the Q&A session at the end of this webinar. But my first question to you quickly, Fabio, it's about what about how to capitalize? I mean, we have seen different business models, I think, for nuclear power plants, but also for project developers and technology providers. So how to capitalize on hybrid business models where hydrogen is not the only product from to be let's say produced using those kind of projects. Electricity and steam also could be foreseen.
Yeah, indeed. So there is, I think, the usual trend has been to use hydrogen as a storage energy vector. That means that you are using the renewable energy over exceedance of production and you use the electrolyzers in that moment in order to store that energy somehow, which is reasonable system, but that unfortunately is not very efficient at the level of capitalizing on the capex of the electrolyzers. As we could see on our slide, for renewable case, the impact of the capex of the electrolyzer is really high. So what we usually suggest is the opposite: to have a source that is baseload producing hydrogen. So when we are talking about a future hypothetical SMR that would produce hydrogen baseload, and at the moment in which it is foreseen that there is Dunkelflaut, or there is a period without without renewable energy sources to stop the production of hydrogen, because the prices on the market are very high in that moment. So in that way, you capitalize a lot on the periods of high energy prices, and thereby, if it is included in the business model, also the price of hydrogen can be kept at for a longer time at a lower price.
Very interesting. Thank you. Maybe my last question to you before we hand over to Nicolas as the next speaker, regarding the demand. So how to compare the hydrogen demand comparing to the future production capabilities and ambitions?
Yeah, indeed. I think it was mentioned that at this moment the demand is not yet there for the ambition that was foreseen of these 10 megatons. However, at least what we see is that the carbonization of a large installation like steel production, they request in the order of hundreds of kilotons per year. So only a few of those when the project of actually full decarbonization of the full process will be actually in place. The demand will be there very soon at the level of these 3 megatons. But what is being observed is indeed that at this moment the momentum is still missing. There is a need for more incentives for both the end users to decarbonize by using low carbon feedstock and on the other side for low carbon production.
Great. So thank you, Fabio. Let's now move to Nicolas from Genvia. Please, Nicolas, activate your camera. Yes, great. So Nicolas, I would first ask you to introduce yourself, introduce Genvia, and thank you for joining us to speak as a technology provider based in Europe, which is working on a very disruptive and very interesting SOEC, electrolyzer. So thanks, Nicolas. The floor is yours. You have 20 minutes. I will be the timekeeper. So go ahead.
Thank you for the introduction. And then, can you guys see my screen? Just confirm that it's okay.
Yes.
Okay, very good. Yeah, so I'm Nicolas Valayé. I'm based out of France, working for Genvia for the past 3 years. Genvia is a manufacturer of solid oxide electrolyzer. I will come back in my presentation with a couple of slides on Genvia. So today I have one part of the presentation is going to talk a bit more about the solid oxide technology. And it's some of these advantages and the role you can have with coupling with nuclear to produce hydrogen. And I have a couple of slides on Genvia in terms of explaining a bit where we are in our industrialization roadmap. Okay. So going next. If I can move next. Yes. So as part of the energy transition, if we want hydrogen to be one of the energy vectors to contribute to the transition and to all the way to net zero, then we need the low carbon hydrogen, and we need that hydrogen to be competitive. And if we think about hydrogen from nuclear power, and here I have 2 screenshots from the Global Hydrogen Review from the IEA. Then on the left, there's some high-level assessment that from a net zero emissions scenario point of view, then nuclear has a role to play along with the renewable power sources, providing some competitive renewable hydrogen or low carbon hydrogen. And on the right side is the emissions level. There's no point in producing hydrogen using electricity that is produced from coal or heavy loaded in terms of emissions. The goal is to reduce emissions, and renewable power or nuclear power bring us that low carbon element that is key to the decarbonization roadmap. That's a bit of the macro context that producing hydrogen from nuclear, as long as it is competitive, it is low carbon, and it will have a role to play. As Félix mentioned, there's a huge ambition in terms of domestic production in Europe. There is limitations in terms of electricity supply. We need a lot of electricity for the energy transition. So nuclear will definitely have a role to play in the coming years and coming decades. But a bit on the, if we want to produce hydrogen from electricity, so the electrolytic production pathways. So today on the graph here, we have on the left, you have we can do electrolysis, low temperature electrolysis with liquid water. So that's the technologies like alkaline and PEM. And you can see today with the results from the first hydrogen bank auction, most of the projects, 99 or almost all the projects, were using either one of those technologies or a combination of those two. Alkaline is the most mature. It's been used for many decades. PEM is a bit more new, but it has started as well its industrial phase. So both technologies have their advantages and disadvantages, but the main thing it has, we are starting now the industrialization phase and the cost reduction phase. From a world standpoint, we don't have yet, let's say, the return on experience on large systems. So the first large systems are being planned, they are being funded, but they are not yet in operation. So there's still a lot of learning curve to do in terms of scaling up all those systems for large applications. But the technology is there and is mature, and that's why project can be initiated if there's the off-takers are secured. On the right side, what we have is a high temperature electrolysis. So there we don't do electrolysis of liquid water, we do electrolysis of steam, so water at the vapor phase. We sometimes call that as a high temperature steam electrolysis, or solid oxide electrolysis, or sometimes solid oxide cell, SOEC. So you might see all the acronyms. So the rest of my presentation is going to focus a bit more on that technology. Solid oxide electrolysis is less mature than alkaline and PEM. It has a lot of interesting advantages and promise. So that it's on a fast lane for industrialization, but it is require, we are at a lower TRL compared to other technology, and of course we haven't really started the curve of decreasing the cost due to mass production and industrialization. But hopefully that will come in the coming years. What I will add on this slide still is that on the left side, in the context of nuclear coupling, which is the context of this webinar today, you would just connect electricity. So electricity from nuclear connected to an alkaline or PEM electrolyzer. You still need to, you can put that as well for the solid oxide electrolysis, but in addition, you can valorize some heat or some steam produced by the nuclear facility. So for solid oxide electrolysis with nuclear coupling, you do both at the electrical coupling and as well the heat coupling. And I'll come back to why we want to do that with that technology. What's interesting with the solid oxide technology, at the core of the technology is a solid oxide cell that is put in a stack for putting modules to form large systems. So the unitary block, the smaller one, the stack, is actually versatile. So that's been demonstrated, that's been used for most of the solid oxide players. So we can use the technology to produce hydrogen. In that case, at the inlet, you have steam and you have electricity. You can also use the same let's say stack, same equipment, same core module in fuel cell mode. In that case, we talk about solid oxide fuel cell. There's different type of applications, in particular for maritime. There you basically supply a fuel. The fuel can be hydrogen, could be ammonia, could be methane, or methanol. And then at the exhaust, you generate power, electricity, but you also generate heat. So the efficiency of in fuel cell mode is quite good, even if you just use the power. But if you're also able to leverage the heat, then you have actually a very efficient system in terms of energy efficiency. If you design a system around that stack that leverage both modes of it, then you can have a reversible system. It's called the RSOC, reversible solid oxide cell. There you can envision some use case where potentially you would produce hydrogen when you have excess energy on the network, on the grid, or solar energy, and then you would when you don't have that energy as a source and you want to produce electricity back on the grid, then you can be using that in fuel cell mode. There's a fourth use of the technology, which is kind of an extension of the hydrogen production, is that you do co-electrolysis of CO2 and water. So at the inlet of the technology, you have a CO2 feed, you have steam, and you have electricity. And at the outlet, you basically get syngas, so carbon monoxide with a mix of hydrogen. And that is a very interesting break, especially in the context of synthetic fuel production, because it allows to have the right stoichiometry to produce, for instance, e-kerosene via the Fischer-Tropsch pathway. And at the time, you can also reduce some of the complexity of the overall plant system, because you don't need to have a reverse water gas shift brick in your e-fuel plant design. So that's the kind of the four applications. There's many. There's been a lot of focus in industry on the fuel cell side in the past years, and now there's a more emphasis on producing hydrogen using the same technology, and that's what Genvia is focused about in the short term. Going a bit deeper on the technology, but I won't go deeper than that. I promise that all the rest of the presentation will be a bit less detailed on the technical side. So the one important thing on the technology, it is ceramics based, so it can scale. There's no expensive material like platinum in the technology, so it is really scalable in terms of the material it's used at the heart of the technology. You inject steam at the cathode, you get hydrogen back, and then on the anode you have an air strip to help kind of move out the oxygen which is produced on the other side. So that's kind of the core of the technology. The graph on the side is actually a thermodynamic graph, and I'm going to use it to explain a couple of things, because the technology, the promise of fluid oxide is actually up to 30% electrical efficiency compared to low temperature electrolysis. In other words, you need 30% less electricity to produce the same amount of hydrogen. So, and given that 70 to 80% of the cost of hydrogen comes from the electricity, that is a game changer in the electrolysis world. So that's why this technology is high on the agenda in terms of industrialization. But this 30% gain comes from two things. So the first thing is that here this is the total energy to create the molecule of hydrogen and oxygen out of water. And there's this stage of generating steam. So the vaporization stage of liquid water to steam, if you have an external source of energy that you can valorize to create that steam instead of electricity, then you save about 15% efficiency, electrical efficiency. The other piece is that at high temperature, when the higher you go, in a way, you can replace some of the energy required for the electrical chemical reaction. Instead of using electrical energy, you can use heat instead. So the heat dissipated or the heat generated by the electrolyzer, then for fluid oxide technology, then that's part of the reaction. So the bottom line for us, for Genvia, we are operating about between 650 and 800 degrees. That's a choice that was made for technology that allows some compromise in terms of the quality of the steel for the equipment. Doesn't have to be too sustained too high temperature, and also the capacity of the technology to have a higher density and scale up the production of hydrogen. So at the heart of the technology, the temperature of the steam will be at around 650, 800 degrees. And as we produce hydrogen and air enriched oxygen, we're actually reheating the steam that is used at the inlet of the system. So the bottom line here is that for solid oxide electrolysis, what we need let's say from a boundary system, we need enough heat to produce the steam at around 120 degrees, 150 degrees. And if we have that, then the system as a black box takes care of putting the steam at the right temperature and that cooling down the fluid at the exhaust. So that's what I want to say on this slide. So 15% from efficiency on valorizing an external source of heat, and 50% less electrical demand because we're able to leverage the heat produced from the system. That can be summarized a bit in that graph here. So for solid oxide electrolysis technology, you need about 39 kilowatts of electrical input per kilogram of hydrogen at the inlet of the system. You need about 9 kilowatt thermal input to produce that steam. and there you go. You have your molecule of hydrogen with the, and then you do have a bit of residual losses. And low temperature electrolysis technologies, the electrical input to the technology is about between 50 and 60. They do, of course, produce the same molecule of hydrogen, but they do have to get rid of the thermal losses that is part of the technology, which Genvia can valorize with the solid oxide electrolysis. So the bottom line there. So if you have low carbon electricity, if you have a source of heat to produce the steam, whether it is coupled with a nuclear or generated from a nuclear source, or it comes from an industrial setting, and the heat you have access to is, of course, cheaper than electricity, or cheaper than what it would cost to generate the steam through electricity, then you improve your SOH and you basically have this higher efficiency of the system. So that's why I'm saying that the solid oxide is definitely the preferred technology to couple with nuclear for the production of hydrogen. Now, if we talk about producing hydrogen is great, but we have to think about also applications of it. So applications where we do have heat coming from industry. So that's the left side. So solid oxide is also kind of a preferred technology where there would be lots of heat that is not necessarily valorized in an industrial process. So as example, steam, chemicals, ammonia production, methanol production, the refining, heat industries, glass production, aluminium. So all those they have in their processes, they're trying to electrify. They are somewhat part of the process, but not everything can be electrified. And they still need gases to reach the desired temperature. That's part of the process. And there, Genvia or solid oxide technology can be a source of use of that heat and produce hydrogen at a lower cost and at a better efficiency. Another use case, not necessarily bigger, but another use case which has a bit of momentum these days, in particular thanks to in Europe because of REPowerEU and the drive to decarbonize the maritime and the aviation sectors. So for synthetic fuel, the process of producing ammonia, Haber-Bosch, or methanolation process or Fischer-Tropsch process. So those are exothermic, and the solid oxide technology can use some of that heat to produce the hydrogen needed by the process, and thereby improving the efficiency. And in terms of production, I already covered a bit of that. If we don't have enough heat from some of those processes, or we are maybe in the context of a hydrogen hub, but then coupled with using nuclear source to provide the base load production of hydrogen, then obviously we can leverage either some heat or steam generated by the plant at a better efficiency than if we were using electricity somewhere else. So definitely some advantage there. As mentioned earlier, that solid oxide technology is a bit less mature. So the key factors that we are focusing on as an industry, and Genvia as well, is to keep lowering the efficiency, the electrical energy needed for each kilogram of hydrogen by maximizing the use of the heat. But technology is great, but you need to be able to manufacture it. So lowering down the cost of each unit, so the capacity of production, scaling up manufacturing, and introducing, let's say, fully automated manufacturing, so to reduce the effects, to control what you produce, and to reduce the degradation of everything. And today, solid oxide cell are known to have there's some area of progress is the duration of the lifetime of the technology. That's something that obviously everybody's working, and there's roadmaps to achieve better lifetime. But at the same time, if you produce those components very cheaply, then we can just consider them as consumable of the project and be part of the normal operation in a bigger plant. A couple of words on Genvia before I give back the microphone. So Genvia, we are a public-private partnership between five partners. We are based in France. Our mandate is to mature and industrialize high-efficiency solid oxide electrolyzer using technology developed for the past 15-20 years by the CEA in France. It's a leading research center. The two largest shareholders is the CEA and SLB. It's ex-Schlumberger. We have three other partners: the inventor of cement, Vicat, and the group Vinci, and we also have the Harris Occitanie. So this is a region in France who has invested also in Genvia. We were able to start. So the company was created in March 2021, so a bit more than 3 years ago. We were able to start very quickly because we had a lot of employees seconded from the parent companies to join, with a lot of expertise joining in very quickly. We are a laureate of, we are part of the EPCI in Europe, hydrogen, the Wave 1 I2 Tech, both on the fuel cell and the hydrogen production. We are one of the 10 projects with a strong support with one of the 10 projects supported by France, and we are grateful for the support. We have 3 sites in France, manufacturing in Béziers in the south, R&D in Grenoble, co-located with the CEA, and engineering in south of Paris, co-located with the engineering center from SLB. Just a couple of things on achievements. So we were started as a company. We were founded in March. We were lucky to be able to leverage a building that was made available to us, a large facility in a plant where there is already some manufacturing from SLB. So having access to, let's say, to land, to already the structure of a building, and a lot of competence for manufacturing 4.0. So 6 months later, part of the building was dedicated to a workshop where we had the transition, kind of the technology transfer from the lab to the industry. At the end of the year, we were able to produce already our the first edition of our second generation stack in Béziers. After that, we converted that workshop into a module assembly facility, and in the rest of the building, we developed our R&D pilot line, which we inaugurated last year. That pilot line produced the stacks that are needed for our own development, own income development, and also they will be producing all the stacks that we will need until we have the fully automated lines from our gigafactory being operational. So we are working these days on deploying our first, let's say, system out of our building. We have a system deployed in ArcelorMittal in 2025. That system is being tested, is going to be tested in Grenoble as a replica without the heat integration from the industry. And then, and also it will be, each module will be factory accepted and tested in Béziers using the same configuration. We know that this is more an R&D prototype for us to, as a learning exercise to validate our model, to understand all the issues and to optimize further. But we know it is not the right architecture for large systems. Genvia, we have an ambition to be a large player with providing very large system for large use case. So this is a step in the right direction, but we're also working in parallel on the second generation of demonstrator after that. And then just to conclude my presentation, I'm just going to say that on the nuclear coupling side, on the right side, you have a concept illustration from the new world SMR in France. But for today's nuclear reactors, so regulation is different in the world. So at least in France, you don't necessarily make change to an existing setup, but in other places in the world, if you are able to have a thermal network out of an existing plant, then we can couple the solid oxide technology, even if temperature is below 200 degrees. For new concepts, for new plants, especially SMR, then we can couple with at 150, 200 degrees. And for other generations of modular reactors in nuclear, you could envision different type of couplings. Some are advantageous, some are disadvantage, but there's different options that can be explored. And with that, I will give back the microphone to Aymen.
Thank you, Nicolas, for those insights, great insights, and thank you for respecting the time frame allocated to you. Quick 2 questions, same thing like with Fabio. And again, for the audience, please feel free to keep asking your questions at the Q&A. Don't be frustrated. We will go back to those questions one by one. Quick question to you, Nicolas, then. In your presentation, you mentioned a timeline, okay? Your timeline for your first demonstration project, but also timeline for Gigafactory production line. So can you tell us a little bit more when your technology will be available in the market?
Good question. Thanks, Aymen. So thanks for asking. So as I mentioned, our first generation of demonstrator is being tested now and will be deployed in industrial settings. So we're going to learn a lot from that exercise. And then we have the second one that will come right at the back of it. And at the same time, I put in the slide that the Gigafactory kind of kickoff or FID will be around 2026. And you don't build a Gigafactory in just 1 year. And You also need, your suppliers, and that's a challenge for the industry in general. You need suppliers of equipment also to scale up. It's not just Genvia to scale up; it's also the whole supply chain behind it to scale up. So we do have our pilot line that we have that is operational, that we can produce more stacks out of that line, and that can bridge until the pilot line is ready. But what I can say is that what we see is that the commercial scale up for us will start 2028, 2029, and our ambition is to go higher in system. So the first system is fairly small in size. It is still times 100 the size of what was demonstrated in the lab before Genvia being created. But it's not yet the large industrial system. So we're going to scale up from starting 2028 and onwards on larger systems. But so from there, basically, we can in a way we can take orders. But we know hydrogen projects or e-fuel project takes many years to develop. Probably between 3 and 6 years, the time to develop. So feel free to engage with us in Genvia now with your use case, and we can see whether our technology can be interesting for your project even now or maybe for a future phase in the coming years.
Thanks, Nicolas. My last question to you before we hand over to Dirk. Question on the technology. I have seen in one of your slides, in general, solid oxide electrolyzers are functioning at high temperature. I think that's one of the benefits and the value proposition of SOEC. But you also presented nuclear coupling options in your last slide. Can you clarify whether you require or not high temperature steam at the inlet of the electrolyzers?
Yeah, thanks for asking that, because there's a lot of misconception sometimes that some people understood that solid oxide is a niche application of electrolysis where you need 800 degrees steam or a source of heat at 800 degrees C, for instance, to be able to use that technology, and that's not the case. So if you do have 800 degrees heat to use, then we can make use of that. That's for sure. But the efficiency gain we're having is really from going from the phase liquid water phase to the vapor stage. That's where there's this one of the 15% increase in efficiency there. So for us, what we tend to say is that we need a source of heat that is sufficient to produce the steam required by the electrolysis process. So to keep it simple, it's about steam or heat at let's say 150 degrees C. That will help us provide having the steam either at 150 or 120 degrees C. So that is not necessarily, we don't need the 800 degrees temperature to get the technology interesting. Yes. Thank you.
Very interesting. Thanks, Nicolas, for clarifying this myth, let's say, of people believing that they only need 800 degrees to start producing hydrogen from SOEC. I'm glad to hear that as a technology provider, you're confirming that it's not the case. And once again, I'm personally, and I think the nuclear industry is happy that SOEC technology providers are active in Europe. Now we have seen Genvia. In the next presentation, you will see combination with Topsoe, the Danish SOEC technology provider as well. So thanks once again, Nicolas. And let's now move to Dirk. Dirk, please, can you activate your camera? Dirk is the CEO of ULC-Energy. They have run recently very nice feasibility studies with Topsoe and Rolls-Royce using SMR from Rolls-Royce to produce hydrogen. So thanks, Dirk, for joining us, and the floor is yours. I will be once again the timekeeper. You have 20 minutes. Feel free to share your insights. Thanks.
Thank you for the introduction, and it's a pleasure to present to this forum. I'll start immediately with telling you what we're seeing on this picture. This is essentially the topic of our study. I will not go as far as calling it a feasibility study. I'd probably look at it as a scoping study that wants to give some direction at the possible economics of nuclear hydrogen. What we see in the background are the two Rolls-Royce SMRs. As you will see, and I'll elaborate a little bit in the next slides, we have selected Rolls-Royce SMR as being the lowest risk, nearest term scalable, rather large SMR. And And what you see in the foreground here, sorry, on the side here, you see the cooling tower. I saw one of the questions on the Q&A already coming in on cooling necessity. We are typically assuming, particularly for inland deployment of these SMRs, that we need a cooling solution. We don't like the large towers, so we put in a mechanical draft towers. And on the, I'm kind of trying to going around with my cursor here. This is the Topsu solid oxide facility with the stacks all lined up neatly. And then you see some cooling and you see the balance of plant activities next to it. I will go into a little bit more detail on our project, but I wanted to start maybe giving a quick introduction to what ULC is. So we started ULC about 3 years ago with a mission to realize new nuclear generation capacity in the Netherlands. Both me and my co-founder are Dutch. We have a very long history in energy. Quite a big component of that was in the nuclear fuel markets. And at the time we started, there was too little mentioning of new nuclear capacity in the Netherlands. We're very, very pleased that that has changed materially. And we believe that we have a solution that fits into that space very well. So we believe it's safe, it's reliable, it's clean. This forum, most people will agree probably. But what we went on to do is saying what is going to make a nuclear deployment a success. So we very deliberately chose proven technology. For us, that means a light water reactor solution. We wanted a highly modular delivery solution. We believe that manufacturing large pieces of infrastructure, large projects, going way beyond power plants, going into airports or sluices or anything that's a little bit sophisticated, we are not that great at anymore. And where we found the solution is in modular and factory manufacturing. We also were looking for a very rigorous focus on reducing risk on the execution side and improving economics. So for us, it doesn't have to be perfect nuclear engineering. It needs to be the best nuclear power plant from an economic perspective. Safety being obviously of paramount importance before you even start, but economics coming very quickly after. We're looking for cheap energy. Our philosophy is also meticulous planning. We don't want to rush anything. We don't want to cut things short. So even though we believe we can deliver this solution at the early part of next decade in the Netherlands, we are going in a very steady, continuous pace. So we're not doing this by ourselves. ULC-Energy is a project development company, and essentially what we do is we bring together all the parties that are involved in the realization of a nuclear power project. We've put in place a number of strategic agreements. We actually started off on the spent fuel management strategy and recycling strategy. We want to take full ownership of the full cycle. We selected Rolls-Royce SMR. We have an exclusive arrangement with them for the Netherlands. We also have a cooperation agreement with Constellation, the largest producer of clean energy in the US and operator of 23 nuclear reactors there. And we have recently signed an agreement with BAM Infra, which is the largest construction company in the Netherlands, who is working with us to deliver these Rolls-Royce SMR solution in the Netherlands. So one of the key differences that when we look at, and this kind of links into the hydrogen space, is we very strongly believe that traditionally the way we've thought about nuclear is probably not reflecting the full potential, particularly not in a decarbonizing world with much higher sources of intermittent energy in the system. So traditionally, and even on the existing formal plans of the government and our research organizations, when people think about how can we fit a nuclear power plant in, people think it needs to have a high load factor because it can, but also it's an expensive piece of equipment, so it needs to run all the time. And it's only delivering electricity on the grid. And this is where we said, no, that's not the way to look at this. A nuclear power plant in the first instance produces heat in copious amounts, very reliably. Then we can put that through a turbine to make electricity, so we can deliver heat and electricity. And what we've said is hydrogen is not only a potential energy balancing tool, but we also have a significant hydrogen footprint already. And my numbers are very much Dutch, so I apologize for the European setting. But in the Netherlands, we produce and consume about 1.5 million tons of hydrogen every year. And when you think about it in energy terms, it's a very, very significant quantity of hydrogen that we're using, primarily for industrial purposes, of course. The demand for that hydrogen is 24/7. What we think in this space is that when you start thinking about how you include an SMR, and that's what we try to put in this graph, is this SMR can switch between delivering electricity to the grid, delivering electricity and steam to an electrolyzer to produce hydrogen and oxygen, but also potentially delivering low temperature heat into district heating and slightly higher temperatures. We don't go to the very high temperatures with our PWR into industry. So we have the flexibility to operate baseload at up to 95%. We can completely load follow with our SMR, but our philosophy is let's try not to load follow, because load following implies that we're not running our SMR at maximum capacity. But what's really interesting is this last point, which is we can switch extremely rapidly between the producing hydrogen when we combine the SMR with a solid oxide facility and power to the grid. And to put that in context, the current energy strategy in the Netherlands, and we're not alone in this space, there's other Northwestern European countries that have the same strategy, is let's take the excess electrons when renewables are copious on the net, it's sunny and it's windy, and let's make green hydrogen. Let's store that because we don't have use for it at that moment in time because there's enough power, but let's then combust that in hydrogen-ready turbines at the time when there's no wind or solar. What we're saying is, well, let's actually turn that around. Let's put the nuclear power plant next to a solid oxide electrolyzer. Let's produce attractively priced hydrogen. And then let's switch off the electrolyzer at times when the grid is really desperate and therefore prices are high, and I can deliver electrons in the grid, which will ultimately improve the economics of my facility. So this was exactly the topic of a study that we conducted. Of course, I want to pay full respect to our technology partners. Topsoe we brought in as the Danish technology company with their solid oxide cell technology. Topsoe has been working on this for a considerable time. They've started working on their 500 megawatts capacity factory in Denmark. And it's been very exciting to work with them on what this technology can do. Of course, Rolls-Royce SMR, very modular, pressurized water reactor. From a nuclear perspective, it's what we want it to be, which is relatively boring and straightforward. The uniqueness of Rolls-Royce is in how the project is delivered and the extent to which the power plant, the complete power plant is delivered in a highly modular way. Which we think addresses a lot of the risk and execution timetable challenges. Rolls-Royce SMR is the only SMR that is currently going through a regulatory process in Europe, and that's in the UK, in their home country. We expect them to finish their step 2 in due course this year and immediately go into step 3, which is their final generic design assessment step. I've explained a little bit about ULC-Energy. We were the project coordinator for this exercise. We solicited engineering and costing support from McDermott. McDermott is a large EPCM contractor, engineering services, US headquartered, but they have a very significant presence in the Netherlands. And for the valuation of the flexibility value, i.e. the value of curtailing hydrogen production and delivering power to the grid, we used a company called Kios. Kios is a company based in the Netherlands that specializes in valuing cash flows, particularly from renewable and/or battery projects in this dynamic market that we live in. So this was exactly the type of skill set and a company that has those market-based models that we require to do that valuation. So why did we look at this? So first of all, we wanted to look at two phases. One is, let's just look at how low cost can we make hydrogen. Let's assume it's just base loading on hydrogen production. How low can we get that cost? And essentially the thought is you put it next to a current consumer of hydrogen. It can be set up off grid. You can avoid a significant amount of grid costs in that space. You have the 30% upside in electrolysis efficiency. We've seen that in the previous speaker. It was the same number. And the interesting part is that the steam can be delivered directly from the the SMR in combination with the power. So it's a kind of a standalone unit that produces baseload hydrogen. And then we looked at this opportunistic electricity supply. And the interesting part there is the extreme responsiveness of solid oxide technology in being able to ramp up and down. So what did we do? We basically received the SMR and solid oxide cell CapEx and OpEx inputs. In some cases, we've also had to complement the OpEx numbers with kind of benchmarking it in other industrial processes. But the main input there was provided by Topsoe and Rolls-Royce SMR. The integration between the SMR and solid oxide, apart from electricity, is the heat integration. So we've optimized where do we take the heat from in the reactor, and how do we optimize that heat exchange into the solid oxide. We had to cost the balance of plant, which is the balance of plant for the solid oxide and the heat integration between the two. We then developed a cash flow model to determine the price of hydrogen, at which stage the NPV of this project is zero. And that's essentially representing the cost of hydrogen that we calculated. The second piece was the development of the market model. We put our market model out to 2050. We didn't go very much further beyond that because we thought 2050 was the right time. And we looked at the assessment of additional revenues for these opportunistic sales of electricity into that marketplace. That model is an hour-by-hour model based on a whole wide range of weather data. And as you can imagine, those calculations get quite complex. This is why we also brought in Keels to undertake that work. In the end, what we decided to do is, rather than have additional revenue, we've allocated that additional revenue and deducted that from the cost of hydrogen production, in which case you obviously get a lower cost for your hydrogen production. We also have to realize you produce less hydrogen because you've curtailed your hydrogen production in part. So what did we confirm? We confirmed that in our baseload hydrogen production mode, we can produce at just below €3.50 per kilogram. That's 2024 euros. And when we do this opportunistic operation, we can bring that cost down to below €2 per kilogram, 2024 numbers. And what you can see is that the value of that flexibility, of course, this is based on modeling of future flexibility. You have to always take that, like the disclaimer on your credit card, with being subject to assumptions, and the real life is going to be different. But the input that went into that assessment, we put a lot of work in validating that it's a reasonable volatility that we're introducing. What the study also confirmed was that Rolls-Royce SMR, both Rolls-Royce SMR and Topsoe, are very modularized and factory-delivered technologies. That means that the scaling part of this is going to be easier than with any form of stick-built or alternative traditional construction methods. We can deploy this at scale, but also we can smoothly integrate it into existing and developing energy systems. And what's really important in this space is that what we're seeing, at least in the Netherlands, and I think it's starting in several other countries, is very, very severe grid congestion challenges. And the high degree of intermittent energy on our system is causing a lot of challenges. Essentially, the way we organize our grid and the actual amount of copper that we have in the ground and also the rules on how we connect people are not necessarily fit for purpose, and we're struggling. The nice thing about this solution is you can stick this into an industrial area and essentially not required to interface with that grid. And where you are interfacing with that grid, you will only be using that grid when it wants you to be there. So delivering electrons in a market where there are very few electrons, that's the moment we want to sell electrons. We won't have a necessarily grid connection. At least everything is very location specific, but that's the high level thought. That's also kind of the point about relieving grid congestion, because we can avoid the bottlenecks in the system and make that part easier. And we have an optimized heat integration. So to the previous speaker's point, we have confirmed that we don't see any significant benefit in having higher temperatures. And that's essentially because in the solid oxide process, you have your heat recovery from your exhaust gases. So we assessed what is the demand for hydrogen. Well, there's very few cases where you need hydrogen at 700 or 800 degrees. And very likely you're going to have to cool that down. Well, we cool that down by heating up the steam to operating temperatures. So it's a very important point that we confirmed as well. This is another picture of the stacks and the so you see in the foreground a little bit more zoomed in on the top two stacks, in the background the Rolls-Royce. So thank you.
That's great. Thanks, Dirk, for being ahead of schedules. Really nice insights and information with all of us. I think it's good that we're seeing feasibility studies and the first projects happening in Europe, combining nuclear, whether SMR or maybe existing nuclear power plants, and hydrogen SOEC technology to produce hydrogen. So quick questions to you before we start the Q&A session. We have from questions coming from the audience. So quickly, Dirk, we hear a lot about the combination of high temperature advanced reactors in combination with high temperature electrolyzers. So this is all about, right? But you are using more common PWR technology in your studies here, which is delivering, let's say, around 300 degrees Celsius of steam. What is your perspective on the benefits of higher temperature? I know that you said clearly the conclusion now, but I would like to hear more about your perspective.
Yeah, so I think so we've made a very deliberate conclusion that for commercial deployment, we need to pick a nuclear technology that is going to be licensable and is commercially ready to be deployed. So we think there are a few very interesting nuclear technologies that are being developed. What those nuclear, and that's a whole bunch of different types, like molten salt reactors that can go higher temperatures. We've got gas-cooled high-temperature reactors, TRISO-fueled. They have some fantastic benefits. In some cases, it's because of the temperature profile. In some cases, it's because they have a cooling solution that doesn't need water. And so we need to continue the development of those technologies. What we very distinctly concluded is we don't need those technologies for high temperature for hydrogen production. And so what we very deliberately selected is Rolls-Royce, because this nuclear technology is ready to get licensed. We know what the European regulators are going to insist on in terms of what they need for safety, what they need for containment, what they need for fuel management. Furthermore, for the Rolls-Royce SMR and PWR technologies, the supply chains for equipment are there. We need to scale them up as an industry if we start building more, but we know how to do it. We just need to do more of it, and we need to scale it up. So when you think about that for technologies that don't have that operational experience and the established supply chains, the delta to move from where we are today to where we need to get to for commercial deployment. And commercial deployment doesn't only mean I've built it and it works. It means the energy coming out or the products coming out are cheap and reliable. And I think that's what PWRs have proven themselves to be, is reliable and very consistent. We think with the modular construction, we can also make sure that the project execution is managed and CapEx is kept under control. And then with the flexibility of this tool in combination with things like hydrogen, we're going to see that the business case for this type of deployment is a complete game changer. And what the important thing is that we don't just look at it from a hydrogen perspective. And that's also my feedback to nuclear or the hydrogen initiative. Essentially, we should have grid operators sit here as well, and we should have baseload electricity users to sit here as well. Because one of the products that I can sell out of this situation is that 15 and 20, 30% of the time that it's not sunny and not windy on the system, I can deliver that power, and I'm happy to entertain a contract. And that's the integrated way of thinking is not something we're naturally set up to do.
Great. Thanks, Dirk. My last question to you is regarding the study you just conducted with your partners, Rolls-Royce, McDermott, and Topsoe. Have there any surprises, let's say, or results that you did not anticipate?
Not so much that we didn't anticipate. So it's always interesting to see what the number is that's going to come out, and the number is a number. I'm the first one to say this is a model, and therefore it gives us guidance. What we did also is the model is the study was it's a privately funded study, which is essentially confidential. I've had a lot of requests to share the report. If you are interested in this report, please contact me. I can have a discussion around it, but it's not a publicly available report at this stage. It's been made available by 12 partners that are not named. The thing that I found really interesting is that the modeling work that we did with Kiels, looking at what is in the energy models and visualizing aspects like cannibalization of wind and solar in these energy systems, but also the value of this flexibility, give tremendous insights to what the value of nuclear energy is for industrial purposes. And so when you look at value, what is the megawatt hour worth? We always look at what is the levelized cost of something. But what we should also look at is what is the level. If the product is exactly the same, like a kilogram of hydrogen, it's fine. But hydrogen also has the problem that it's not easy or cheap to store, and we're going to have storage capacity challenges. So whether you're producing that hydrogen baseload or whether you're producing it when there's renewable capacity available or when there's a ship coming in, those elements are going to feature heavily in our future system. And that is probably an insight that, at least for me, kind of poking around in an Excel model that can visualize those things has been very, very insightful. And it's something that it's complex, so you need to spend a lot of time thinking about the issues, but it's extremely valuable insights because it shows what is the value of a megawatt hour nuclear baseload or a kilogram of hydrogen baseload. And having that insight is powerful. It's not all about cost.
Okay. So thank you, Dirk, once again for sharing the outcome of your studies. And I'm really happy that we were able to host, to have you joining us here at this webinar, because we're talking about domestic hydrogen production in Europe, and of course the role that nuclear can play, because nuclear historically has been very well developed in Europe, and we have so many nuclear fleet available that could be leveraged. Your example is of future SMRs, which is actually once again great benefits and great potential. So let's now open the floor to the Q&A session that the audience has raised within the speaker's presentation. We will try to go through all of those questions one by one. We will start by the first asked questions up to the last ones. Yeah, so I think the speakers has already, and some of my colleagues has already started, like Emmanuel has already started answering some of your questions. But I will go through one of them. I mean, through them, and we will try to answer all of them. So there is a question from Jan Rebergen around thermochemical hydrogen generation also. And he's saying, let's say, nuclear could also play a role here, has the potential to be much more efficient with sulfur iodine cycle of copper chlorine cycle might be possible. So I know it's investigated in Japan. Any thoughts? I don't know if I think Nicolas or Dirk, you have had the chance to take a look on this question.
I can have a go at it.
Yeah.
We have not looked at it in any detail because my and I don't know too much about it, but my understanding is that temperature levels for this process are much higher than what we can cater for with current kind of commercial technologies, and that kind of discounted the possibility for us at this stage. So I think for us this is something we can look at if you have a commercial high temperature solution that can accommodate it, and then we have to look at economics because I'm not sure what the cost will be.
Okay, Nicolas, any thoughts?
Well, not on this one. It's out of my expertise, so yeah.
Okay,
I think there's a lot of answers already there. Yeah.
Okay.
Yeah, I want to point out that indeed from JRC, with Professor Fitterer, there is already some quite good answer on the chat.
Okay.
On the Q&A, I mean.
Okay, Dirk, you can keep your camera. I think we need you. I think it will be dynamic. There is a comment from our friend Chris Lefrère. He was one of the speakers in our webinar number 2 around the CFD auction revealed. I mean, I think about the costing, Fabio, that you have been sharing. Any comments on Chris' comment?
Yeah, so indeed, it's when we talk about what we wanted to show, especially with that graph, was the impact that it has, the low capacity factor, despite having a quite low LCOE. Then, of course, the LCOE is not the whole story, and there are some other questions up in the chat that are putting forward the not the levelized cost of electricity, but rather the levelized full system cost of electricity. Of course, when if a hydrogen electrolyzer, if an electrolyzer is taking the electricity from the grid, we'll have to pay the price and the price from the grid. And you know, I'm not an expert on that, but it has to be possible in the future for making direct connection behind the meter, so that so that at least the supply to the electrolyzer is direct, and a base load production without having to produce inject on the grid and then taken from the grid, but there is a direct connection. While for the cases in which there is a need on the grid to have additional electricity, to then inject that as a grid as a sort of additional capacity source for the grid, which has a huge value in the grid of the future, which with a high penetration of intermittent renewable energy sources.
Okay. Thanks, Fabio. Let's go to the next question from Jan. Jan, he's asking about the combination of nuclear power to produce synthetic fuel. And he's asking whether the oil and gas industry is interested. I have seen your answer, Fabio. Would you like to add anything?
Not in particular. Fortunately, well, I can say that Tractebel indeed has been involved in some pre-studies for refineries. So the possibility of decarbonizing with the help of SMRs co-located close to the plant. Indeed, one of the key takeaways is that there are. It's already the first time that the petrochemical sector is looking at nuclear, so it has to be taken in a step-by-step approach. So first thing, putting a reactor for the plugging. They are also using in some cases steam, not even a high temperature steam. So let's say supplying steam from SMR, so that's a feasible thing. But in other cases, they have to replace fire heaters, which require indeed conversion with other thermal vectors. So either steam again, or rather thermal oils that would carry the nuclear heat, let's say, until the process. And it's we are talking about complex modifications that refineries would have to spend big capex on. So a step-by-step approach is the only way to get there.
Okay, maybe I can share some quick thoughts on this point. As Westinghouse, we are also, we have been approached by oil and gas industry to decarbonize. I think the oil and gas, they do have something very confirmed, which is the demand. They have a big demand of hydrogen, and they have a big challenges, let's say, to achieve to decarbonize, and nuclear, and especially the SMR industry coming from nuclear industry, could be a very nice solution, a game changer for them, because it could be located next door to their refinery, and then it could be leveraged to decarbonize, whether directly through hydrogen or through the heat. So that's my quick answer to you, Jan. Let's move then to next question from Sopila Oli. How are the, yes, I think this one was a comment on the deindustrialization of Europe in the recent decades, and how nuclear and the hydrogen combination with nuclear could be a reason to reindustrialize Europe and create a new high-skilled jobs. So any comments, Fabio, on this?
No, I have to say that I didn't delve so deep into the societal aspects of it. I believe that it's an important one, and I've made a small research, let's say, on what has been the latest period. So the graph that you've seen on the map, that was since the creation of the EU as we know it today. There are some data from previous times, for example from France, where you can see that this deindustrialization has unfortunately been ongoing since as long as the data is there on statistics. So indeed, the overall through the last century loss in value has been higher than that. Now the association between that and the amount of jobs suggested to read the report to understand better.
Great. So thanks, Fabio, once again. And I need to find the questions. So the next question is from Chris. I think it was a comment on.
Yeah, I believe that was also related. It's somehow part of the previous
yes.
Answer that I gave. I believe it was a bit of a specification of the previous question. So I think I answered that. If the answer is not complete, I invite Chris to again ask later on.
Okay, so let's then move to the next question from Vanden Pungrat, I think. He's talking about the cooling demand from nuclear, and he's asking whether there will be lack of inland cooling not drive nuclear to near shore location. Okay. I could not understand very well the question.
So the question is, will we have enough water inland for a lot of nuclear in the future? this is the way in which I reinterpret
Okay, I understand now. Okay. Yeah.
Yeah. So indeed, for large nuclear, well, it is already the case that large nuclear power plants are situated either on the coast or by large rivers. That could be different for SMRs. Perhaps Dirk can also say its point of view on that. But of course, as often in the design, it's already integrated the possibility of air cooling that comes with some cost. But it's like it decreases by several orders of magnitude the amount of water that is requested.
And maybe just to add, I mean, we are assuming that for any inland location you need the cooling towers, which means access to water. We haven't really looked at opportunities where you're looking at air cooling, which hopefully in the Netherlands we can avoid. But what's clear is that we have to very carefully consider water management, not only for the purposes of cooling nuclear power plants, but also the effects of climate change and what it does to dry summers and potential water management with events that to be honest, we've just had, which is way too much water everywhere, which with very high levels. So we need to think smartly about water management. I'm reasonably comfortable that in the Netherlands we're actually quite good at doing that. We just need to integrate nuclear cooling into the water challenge.
If I may add a comment, a bit preaching for my choir, is that for solid oxide technology, we can leverage some of that heat, so there would be less waste heat to dispose of if the project use 100% of solid oxide electrolyzer, or maybe complementing a base load of mixing electrolyzer technology in the project. And I think now, especially with SMRs, you have to look at the integration within the local ecosystem and trying to, before maybe for large power plants, there was no, that thought wasn't there, but now we are trying to make use of every calorie we can get, and there may be usage and that can be done instead of cooling things to the air. There may be some alternatives to reusing a maximum of that heat for industrial purposes or residential areas or other use. But I guess there's so much you can heat up the local pool. Yeah, lots of heat.
Okay, so thank you all for I mean, debating about this question, which is, I think, the cooling in general. It's a very interesting question for the nuclear industry. Okay, what is? Let's go to the next question from. I'm glad that we have had many questions, and feel free, please, to keep asking your questions. Next question is, yeah, I think it's from Joseph. I think it's talking about technology, SOEC technology in general. I think he believes it's not innovative enough. What with the thermal splitting of water? So, any comments, Nicolas?
Well, I think the answer from Titus is I like it in a way, right? The innovative enough is not necessarily a criteria. The point is to provide solutions for the energy transition. And honestly, we need all technologies, and we won't have enough, and we won't have enough electricity for everything. So all technologies are welcome. The sooner the better for the planet, for us. And if further innovation can bring to industrial scale some technology that can produce the energy we need with lower cost or lower requirements, then the better, right? All great. And I think everybody has to play, bring their part of the puzzle, and hopefully we can complete the puzzle the soonest.
Okay, thanks, Nicolas. And then another comment and question from Jan regarding synthetic fuel and using nuclear for that and for the aeronautics application. I think I confirmed to you that there is a lot of interest, and as Nicolas was saying at his presentation, that there is a momentum about synthetic fuel. I confirm that there is an interest from the end users that have to abate. Maybe Nicolas, you can add one comment.
Yeah, I was referring in my response on the chat that there's lots of material from the e-Fuel Alliance in Europe. That's an organization that has provide good content, so I recommend you might go there. But decarbonizing the aviation is difficult because you cannot capture, like for cement or for a steel plant, you might have a carbon capture and storage or utilization solution, but it's difficult for aviation. The only alternative is direct air capture. So And then the chance we have in Europe, because it's a bit of a chicken and egg thing, we need to scale up technologies to things to become more cheaper, to have cheaper hydrogen, and that makes the economy running faster. And at least in Europe, with the e-fuel, refuel aviation mandate, and also the Fuel EU Maritime, there are some targets for sustainable aviation fuel, for in the case of aviation, of which there's a sub-criteria on synthetic fuel. And I think all that will drive we drive through regulation, it will drive to force things to move ahead. Along with CO2 tax, I think things will start to move ahead. And I think at my level, we see there's projects that are going forward are more in that space than some others.
Okay. I've seen other questions that you guys already replied back, Nicolas and Chris as well, from Jan. And I invite you, Jan, to get in touch with us, with the speakers, or with Guilherme or myself if you still have other questions. I would like to take another question from a different person. Esperu, what are the downside and or the challenges for SOEC?
Yeah, so I think today it's not TRL 9. So we need to materialize what the promise of the technology that was shown on lab or small pilot scale. We need to pass that industrialization phase. So that's really we need time for that, and that's the primary challenge. And then of course it's also high temperature. So there are some challenges operating at high temperature. There are some advantages, but there are some in case of leaks. But we don't want leaks. So there are some. It's more complex. It's high temperature. At the same time, many of the providers of sweet oxide technology, including Genvia, we are atmospheric. Some others do provide a bit of pressurized hydrogen at the exhaust of the, let's say, the black box system, and being not being pressurized as a downside that you need to compress to the required application, to the required use of the hydrogen downstream. At the same time, it has the advantage that a system which is not pressurized has lower, from a maintenance standpoint on operations constraints. It's simpler as well. So I'm not gonna elaborate more on downsides, and challenges. But it's we have a roadmap, and we're trying to go as fast as we can there.
Great. There is a connected question coming from Jonathan. He's saying to add to this question, increasing the efficiency was mentioned, and he's asking about materials. So are the issues with these to do with materials or other technical aspects regarding the efficiency?
Yes. So of course, heat exchange. A lot of things are happening at the cell level. So I'm not gonna go there. And the ability of on the same square, on the same centimeter square of cell to be able to have a higher current density, and some technology choice in the SOEC family, some have challenges so to go up in higher density. So the choice of the CA that they made on the operating range and the choice of material they've used, it has the promise to allow that scale up effect. And depending on some of the choice that some others may have made, then it might be more difficult. So materials, there's a lot of R&D on the material side at the cell level, and of course, for the higher you go in temperature, for some technologies are going higher in temperature range, then there's other problems related to have very high temperature. Yes.
Okay. If you allow me, Nicolas, to add one thing regarding materials used by SOEC, comparing to PEM or alkaline, there is no rare materials. Do you confirm that?
Yeah, we have control of what we're using there, but we don't have the same scale of challenge as that PEM can have. PEM, they have the platinum and a few others, the iridium, and they have also the PFAS challenge. For us, there's a few things that we have control, but there's always a few things we might use for some of the connectors, but the base is ceramics base, so it's very positive from that front.
Okay, thanks. Next question is from Corthels. SOEC electrolyzers are load variation possible? He's asking whether are load variation possible, and if yes, at what rate?
So I didn't cover that in my presentation. Dirk made a few comments on that in his presentation with Top Flow technology. So for Genvia, the technology that was it was shown in the lab, right? We could go from 30% to 100% in terms of dynamic range. I will complement that with two things. One is that you could go. What's important with high temperature electrolyzer is to remain hot You don't want to go down 0 temperature and go up. It takes time to go up to the required temperature. So we want to have kind of always function at high temperature, but you could operate without producing either hydrogen. You could remain at high temperature, consuming a bit of electricity to remain high, and then not producing if that's necessary. For that, there's some safety gas are necessary to be circulated. But once you start producing, then I mean, some have published different numbers. For us, we don't have numbers to, as with the Genvia had from our systems to actually publish, but 30% to 100% is one element. And I will final comment on that is that flexibility is great, but also you have to have the balance of plant to tag along. So if you produce e-fuel, the ammonia doesn't like up and down, Fischer-Tropsch doesn't like up and downs, and compressors, they have limitation. They are best operating at particular loads. So you have to take that into account. And I will add the extra comment that today we talk a lot about dynamic response of alkaline or PEM following trends from renewable, but there's no return on experience worldwide whatsoever on low temperature electrolyzer following the trend on things. There's been labs experiment, but real large scale systems following renewable pattern and having the return on experience on what the impact on the membrane or the equipment, we don't know. It's not yet done. So it's a challenge for the hydrogen industry to bring that flexibility to the grid in the future. We don't hear you, Aymen.
Sorry, we still have 2 more questions. The next one is, what could be the optimum capacity for SOEC hydrogen plant?
The higher the better. So for Genvia, what we aim at is in the hundreds of megawatts long term, right? That's it's a high. You don't want to have a solid oxide is a high temperature system, so you're not going to have that on a. You're not going to have a high temperature solid oxide on fuel cell on a car. It's a different scale. You have other technology. So for us, it's the larger the better. So there's no optimum. It's
yeah. I think there is no maximum.
Yeah.
I think there is no maximum. The only maximum will be the only limitation will be the power availability, whether the heat, the thermal power, or the electricity power. And with nuclear, luckily there is no limit. So as far as the generator, the reactor is producing. The last question I see in the Q&A is from Jonathan. I think it's for you, Dirk. You mentioned in your presentation SMR will not be connected to the grid to save costs. But on the same time, you mentioned the duality. Sometimes you will sell hydrogen, sometimes you will sell electricity. And he's asking, how will electricity be sold opportunistically if it's not connected to the grid?
Yeah, so the way we anticipate that happening is that you don't have a firm capacity connection on the grid, which is the thing that costs money, which means that at any moment of time, you can either deliver or receive power up to that capacity level that you've contracted from your grid operator. What we would have is we would have the physical equipment installed to be able to deliver, no firm rights to deliver electricity. And we would simply put any economics that we need to pay to a grid operator to interruptibly deliver opportunistically when the grid is in need of those electrons. And those economics on a variable basis would be counted into the optimization dynamics of your at the moment in time. So I'm not paying firm grid costs. I have an interruptible connection, and I will just put that into the economics.
Okay, thanks, Dirk. We only have 2 minutes left. I don't see other questions on the Q&A, although some of the audience, unfortunately, they asked questions on chat. I think Guilherme, he copied, and I believe they are now on the Q&A. There is maybe last question here. What do the speakers see as the most important technologically research challenges for SOEC, for SOE nuclear integration development? So the most important challenge, if I ask each one of you for the number one for you, the challenge number one for you, what would be the challenge number one for you, Nicolas and Dirk and Fabio?
Yeah, so the challenge number one for Genvia is the industrial scale-up, but not just our technology, of all the suppliers that goes along for the balance of plant and everything to build the plant. It's not just the electrolyzer, it's everything else, compressors, everything.
Okay. Fabio, for you, challenge number one for this combination SOEC and nuclear?
Well, we speak of integration, and there are a lot of other challenges. So if you focus on the integration, probably it's at the system level in order to optimize as much as possible the use of the electrolyzers, so that they are operating as much as possible at the like base load without much variation.
Okay, and you, Dirk?
I think the biggest challenge is almost in our planning department. So and that sounds like a vague term, but there's a lot of planning and strategy making going on about how our future energy systems, what they need to look like. What I'm finding is that it's very challenging to put this concept of nuclear SMRs that are completely scalable with solid oxide, delivering power, hydrogen, and heat flexibly. And if you start putting this tool into your energy solution, the solution looks completely different from what's on the table right now. And I think that delta, we need to find a way how we make that delta more manageable for us. Because if it's just the argument sometimes this is just too good to be true. And that is a challenge for us because people don't give it the attention it deserves. So I think that integration element of it and making sure there's more people that have nothing to do with nuclear that are sitting on these information sessions is really important. So
okay,
yeah.
Thanks, Dirk. For me, the challenge I see, it's not only technical, and I think you covered very well the technical challenge. The real challenge for me is the lack of support of this kind of use case, which could be should be benefiting from mechanism for support to accelerate roadmap, to solve challenges, to go through lessons learned and integrate that for future projects. So this is, I believe, one of the highest challenge. There is another question from my last. It's going to be the last one, exceptionally from Berg. What do the speakers see as the most important? No, I don't think this one is from. So copy and paste from Clary de Jong. Where are we now as far as it is kerosene concerned? Is it viable to use SMR and hydrogen in the near future in air cargo?
So would be really good to define near future first. Go ahead, Fabio, sorry.
To my knowledge, e-kerosene has been used in small quantities already. KLM, I think, with Shell, they've traveled already with a few hundreds liters of e-kerosene. Now, viable to use SMR plus, hydrogen produced by SMRs. Yes, I don't know, like technically at which level. I think at the level of the quality of the e-kerosene, there is some work to be done. But feasible, I think it is. Being optimistic.
So for me, I'll just say technically it is viable. E-kerosene has been, I mean, the most new airlines, the engines are certified to cope with 50% SAF today, and the industry is working towards certifying 100%. So technically it's there. It's more a question of economic value, the cost of that e-kerosene, and the timeline to get that kerosene on the market. So the SMR's timeline is next decade, and then it's a question of scaling up and having for the e-fuel, hydrogen is a large component, and it's down back to the cost of electricity at the end. We can improve that. There are some area of improvement of the cost of e-kerosene, but at the end of the day, the big chunk remains the cost of electricity and the availability of electricity.
Okay, we run out of time. I would like to conclude. This very nice, informative webinar. We tried as much as we can to raise awareness about this use case, to answer questions, to explain the use case. With Fabio speaking about the trend and the importance of nuclear domestic production and the role that nuclear can play in a very short term to solve the chicken and eggs issues of lack of opportunities and options to import hydrogen in Europe, which is challenging, by the way. So maybe nuclear can help Europe to produce the quantity of hydrogen that hard-to-abate sectors are looking for. With Nicolas, we try to show a case of example of technology providers based in Europe who are really working hard to make this happen in a very, I think, a rational and interesting approach, combining industrial, private, public sector, industrial end users, and technology providers. And last but not least, with Dirk, we try to showcase an example of projects in Europe that might be a game changer for future. We hope that we answered many of your questions. We look forward to having you again in next webinars. On behalf of the Webinar Hydrogen Task Force team, I would like Guilherme to use your camera. Activate your camera, please. And Andrei, activate your camera if you are, if it's possible. I would like to thank each one of the team here, Emmanuel as well, Emmanuel Giraza from NG, Jean-François Dedin from EDF, Jessica from Nucleareurope. I would like to thank each one of you for the support to make this happen. It's a pleasure for me. My name is Aymen, working for Westinghouse, and looking forward to seeing you again many times. Thank you very much.
Thank you very much, Aymen.
Thank you.
It was a
Bye-bye.
pleasure.
Thank you.
Thank
See you
you.
next time.
Have a nice day, everyone.
Have a good day.